Hey, we're talking about applications of matrices and determinants today, and we're going to learn something called Kramer's rule, which is super helpful and actually kind of fun. So let's jump in. Let's talk about some vocabulary. Uncoded row matrices are basically matrices that represent a decoded message. So remember, decoded is not that secret, right? A coded row matrix or matrices are matrices that represent an encoded message, meaning it's a little bit more secret. You have to uncode the message. Okay, so one of the ways that we use this is we can use the area of we can use matrices to find the area of a triangle. So the area of a triangle with matrices x1, y1, x2, y2, x3, y3. We'd say that the area is plus or minus, and now it doesn't mean that it's plus or minus in the way that it could be both. It's plus or minus whichever one makes the answer a positive value. 1/2 times, and then this is how we put the information into the matrix. x1, y1, 1. x2, y2, 1. x3, y3, 1. So again, the positive or minus symbol indicates the appropriate sign to make sure that we have a positive area. So basically, we find the determinant of that 3 by 3 matrix and multiply it by 1/2, either plus or minus, to give it a positive value for area. So for example, if I wanted to find the area of the triangle with these vertices, I'm going to set this up, A equals plus or minus 1/2 times, and I'm going to set up my 3 by 3 matrix. Here we go, -3, 1, 1, second point 2, 4, 1, third point 5, -3, 1. Go ahead and put this in your calculator. You're going to use your calculator just like we've been practicing. Type in a new matrix, make it a 3 by 3, type in the values of -3, 1, 1, 2, 4, 1, 5, -3, 1. Find the determinant of it. So if I take 1/2 times the determinant of that matrix A, I'm going to get 1/2 of -44. So make sure if it's plus or minus, this is going to be a -1/2, because then a -1/2 would be a positive 22. So the area of that triangle represented by matrix A is 22 units squared. Okay, let's talk about what collinear points are. Remember, co means to share, meaning they're on the same line. So collinear points are points on the same line. Okay, so for example, if these are the points x1, y1, x2, y2, and x3, y3 are collinear, they're collinear if and only if this will work out. If x1 Here we go. If x1, y1, 1, x2, y2, 1, and x3, y3, 1 equals 0. So basically, you're going to take the determinant of this and just verify to make sure it equals to 0. So if we're going to determine if these are collinear, first we're going to set up our 3 by 3 matrix. So we go -2, 4, 1, 0, 3, 1, and 8, -1, 1. We're going to find the determinant of that. You're going to use your calculator, where A is your matrix, so you're going to find the determinant of A. And the determinant of A, we do see that is 0. So therefore, and in math, there's like this fancy way of saying therefore. It's right here. It's like a triangle of 3 dots. So we say, therefore, they are collinear. There we go. Okay. So now here we get to jump into Cramer's rule, which is kind of fun. Cramer's rule states that if a system of n linear equations has n variables in a coefficient matrix with a non-zero determinant A, the solution of the system is, so this is for each of the variables, each of these variables equals the determinant of an adjusted matrix over the determinant of coefficient of matrix A. And I'll tell you what that means, but for now, let's fill in where the ith column of I sub A is the column of constants in the system of equations. So we're going to talk about what that means. So for example, if you have, let me just put it this way. If you're looking for x, we're going to take the determinant of the adjusted matrix x divided by the determinant of the coefficient matrix, and the value of y, we would take the adjusted determinant of y divided by the coefficient determinant d. So let me just kind of say, so this here and this d is the coefficient matrix. Okay, and that's really important that you know that. So for example, I wanted to show you, let me go back to this. If the determinant of the coefficient matrix is 0, then the system has either no solution or infinite solutions. Okay, so let's kind of go back to what that looks like. Okay, so let's just say we've got this, instead of a 3 by 3, we're going to practice on a 2 by 2. And we've got this system of equations, 2x plus y equals 7. And 3x minus 2y equals negative 7. So we're going to use those two systems and the Cramer's rule to set this up. So first things first, I'm going to make this into the matrix that we were talking about. Okay, so we can turn this into an augmented matrix, 2, 1, 7, and 3, negative 2, negative 7, okay? Keep in mind, this is our coefficients matrix, and this is our constant numbers, right? Those constants which come from the solutions here. So in order to do this, we're going to find the value of x by taking the determinant of the adjusted coefficients of x, and I'll show you how to do that in a second, divided by d. So in order to find d, the determinant of d is only going to be the determinant of these numbers right here. So of 2, 1, 3, negative 2. So when I do that, we're going to end up with negative 4 minus 3. We end up with negative 7. So that's d. And then the adjusted determinant of x will look like this. So what happens is when we adjust the determinant, we take the solutions, and because we're looking for x, this is our x row right here, we're going to replace the solutions into this x row. So we're going to rewrite that 2 by 2. So instead of the row of x's, which is 2 and 3, and we got that from here, 2 and 3, okay, we're replacing it with the constants, which is 7, negative 7. And then we're going to finish writing the determinants right here, which is 1, negative 2. So we find the determinant adjusted for x, and we know that this is going to be diagonally negative 14 minus negative 7. Add them up, and we get negative 7. So our d determinant with adjusted x is negative 7. So we see x equals negative 7 over negative 7, which is 1. Okay. Okay, let's solve for y now. So remember, we know y equals the adjusted determinant of y divided the determinant. Well, we already know the d is the coefficient determinant. We already have that here at -7. So we're just going to rewrite that same value. We already found it. We've already got our denominator. So all we have to do is find our adjusted determinant for y. So what we're going to do is we're going to find our determinant. Whoops. We're going to find our determinant. And instead of replacing x like we did before, we're going to take our constants or our solution values and we're going to replace them for that y column. So remember, these were the coefficients that we got from our column of y's here. So instead of using those numbers, 1 and -2, we're going to replace it with 7 and -7. So let's write this. So we're going to go 2, 3, so instead of 1, we're using 7 and -7. So let's find that determinant. So we go diagonally as -14 minus 21, and that becomes -35. So that's our determinant adjusted for y. And that -35 over -7 is +5. So our solution, x comma y, is 1, 5. And that's our answer. Okay, so really quick, I just want to show you, I'm going to kind of give myself some room right here. You can put this on the side of your paper, however you want to do it. But I just wanted to give myself, we're not going to go over cryptography. I know you're super disappointed. But I wanted to show you really quick, what if you had to find a solution using Kramer's rule for a 3x3? Okay, well, here's what a 3x3 would look like. We would say, you know, there's some coefficient a, x, a2, x, a3, x, b1y, b2y, b3y. So again, these are just the coefficients in the system of equations, and then you'd have your z terms, and then your constant numbers. So remember, again, this is the matrix that's representing the 3 variable equation where A is the coefficients on x, B are the coefficients on y, C's are the coefficients on z's, and D's are those solutions that are listed or the coefficients. So in order to find any of these, we first need to find the determinant D, which in this case would just be those coefficients. So A1, A2, A3, B1, B2, B3, and then finally C1, C2, C3, whatever those are. So you would find that 3x3 determinant. You could do that by hand, or you could do that, you know, in the calculator. You know how to do it. To find the adjusted determinant for x, you're going to keep the same determinant we have here, but we're going to replace that x column with those solutions numbers. So we're going to go D1, D2, D3 replaces the x column, but everything else will stay the same. So B1, 2, 3, and C1, 2, 3 will stay the same. To find the adjusted determinant for y, we would also keep the same, except for now we're going to change the y coefficients and replace it with the d's. So we're going to replace D1, D2, D3 in the y column, but everything else stays the same. So A1, A2, A3, and this would be C1, C2, C3. Okay, and then lastly, actually let's make this pink. To find the adjusted determinant for z, again, we would use the same determinant as d, except for now we're going to use our solutions and replace it with the z column. So this is going to be D1, D2, D3, and everything else stays the same. A1, A2, A3, B1, B2, B3. So then to find each of these, we would take the determinant of this adjusted dx and put it over that value for the coefficient determinant as well. Okay, I'll see you back in class.